So other than that, what do you think other amplifier maybe? There's something called current amplifier. And fourth one will be output is voltage and input is current. So, I made mistake here. This has to be trans impedance or trans resistance amplifier. So there are four different classes of amplifier. So one of them is op-amp, which is commonly a voltage amplifier whose output is voltage, input is voltage, or its voltage controlled voltage source. And transconductance amplifier, it's voltage controlled current source. Current amplifier is current controlled current source. And trans impedance or trans resistance amplifier is current controlled voltage source. These are different names, right? So earlier we got somewhere where output was current and input was voltage. That is also the transfer function for a voltage controlled current source or an OTA. This is commonly known as op-amp. This is OTA. Yeah. So other than that, we also learn about T kinds of network and pi networks. Right? So you can identify which one is T and which one is pi. And summarizing what we have done it in ABCD parameter or transmission matrix. This is also known as T parameter, where A is defined by open circuit voltage transfer function, B is defined by short circuit transfer function, short circuit trans impedance, C is open circuit trans admittance, and D is short circuit current ratio. And here all the parameters are connected with respect to output or input. There is a ratio, so that's why this is known as transmission matrix parameter, and this is very much popular in antenna theory. Right? So this is what we learn. Let's assume there might be the case where you will see somewhere transformer. So everybody studied about transformer, right? So transformer might be having one side n number of turns and one side 1, so we are writing n is to 1, right? And there is a, like, this side is known as primary, this side is known as secondary, and if this side it's V1 and this side V2, and the current flowing through primary and secondary are defined by I1 and I2 respectively, then what we can write down is V1 is equal to n times V2 and I1 is equal to 1 by n times minus I2. Are you aware of these equations? Yeah. So V1, because of this n turns, you will have n times V2 available at the output. So or you can make it reverse to get the step up. Have you heard about the words called step up, step down, buck boost? So okay, so if it is step up or step down, step up is called boost, step down is buck. Okay, so these are another names. Maybe you have not heard the name, but now you should know these names. So maybe the design will be studied in power electronics. If you want to further go into very high voltage engineering, then you should take power electronics, where you are going to have transformer and thyristor. You heard about thyristor? Okay. Then you will study that. So we are not touching that. Okay. So if these two equations are there, we can write down ABCD parameter as follows, where V1 and I1 in terms of V2 and minus I2 will give you n and 1 by n this side. This is just for your information and you can use it maybe in your future. But if you forget this, then you can always write down these two equations and you can find out the ABCD matrix for a transformer. So now if we have some ZL which is terminated at the output of transformer's secondary coil, then you can write down same equations again which we have written, where V1 is equal to n V2 and I1 equal to V2 by n times ZL. So replacing V2 as V1 by n is going to give you this relationship, and if that is the case, where this is going to give me V1 by I1, sorry, yeah, V1 by I1 is equal to 1 by n square and ZL, which I can call it as Z11, or this is a n square into ZL. Yeah, that is what I wrote.
1 upon.
So V2 is equal to V1 by n. So V1 by n square by ZL.
V1 by I1 is equals to n square.
Oh, you are saying so V1 by I1 is equal to n square, right? That's correct. Yeah. So V1 by I1 is nothing but Z11, or you can say that that's the input impedance looking into this transformer. Similarly, you can find out what is the output impedance. That will be defined as Z22. But in this case, this is the most important derivation, because if we are looking into the transformer, the effective input impedance is going to be equal to n square times, n is nothing but the number of turns, times ZL. So whatever ZL you are keeping, that is going to be available at the input of any transformer. So that will be the input impedance. Without applying Thevenin theorem or other theorem, you can directly find out this, or you can say that if I am terminating the output terminal with inductor, then if I am looking into this, I am going to see n square ZL, where ZL is nothing but L, right? Or if I am keeping the capacitor, you have to apply same thing and you will find out it's C by n square. I am not going into the derivation, but it's simple. You have to go through those two equations where V1 and V2 are given for a given currents. These two derivation might be useful in your future when you are going to study power electronics. Right now, maybe not useful, but for power electronics, these two derivations are useful. Okay. One more thing, if you want to find out the transfer function using Z parameter, you can find out two parameters which are Z21 and Z11. If you take the ratio of these two, which is nothing but V2 by I1 times V1 by I1, right? So both I1 will be cancelled out, and the effective voltage ratio which will be available is equal to V2 by V1. If V2 is output and V1 is input, then the ratio of these two is the transfer function, right? These are the just the equations which will be useful for finding out the transfer function. The reason is, what is the usage of this analysis? We are doing this analysis for mainly three reasons: to find out what is the input impedance of any circuit, what is the output impedance of any circuit, or what is the transfer function, so that I can find out its transient, I can find out its AC response, or others like DC or other also, right? Pole zero analysis, or all the analysis can be done if you have the transfer function. And Z in and Z out will decide the type of amplifier, and this will allow you to connect two amplifiers together. If there is an amplifier which is voltage control current source, and there is an amplifier which is current control current source, you cannot directly connect them together, right? Either you need to, okay, this is not output is right. So you need to convert this current quantity to voltage, or you need to do some buffer or something which will not cause any problem for the current driving, or there is no loading effect. So for that we need to find out these things, and that will tell you the dynamics of your circuit. So through this one you can find out this. Similarly, using y parameter, you can find out transfer function if your y21 and y22 are available, similar to what we were doing in z parameter. The question which I am keeping to you people, you have to find out why it is minus. Right? This is your home task. It's very easy, but you have to keep the equations. Maybe you can go through Friendly and Co and you can find out why it is minus, but it will give you the ratio, right? One more thing, sometimes like just for the completion of the chapter, where if you want to find out the transfer function of a network where the output is terminated with a resistance, this is the real situation. This resistance might be the load resistance. By the way, do you know what is the load resistance, or what is the significance, why we are keeping load resistance? How to decide what value of load resistance has to be there? Let us assume that you people are working in design practicum and you are designing something with some motors somewhere. These motors are connected by my Arduino board. There is some output somewhere, something is there. So can I connect this one here directly or not? Or let's forget it. So how to decide what value of load resistance should I take? Because first, when you are doing the measurement or the experiment, you are measuring standalone. Here, let's say you are getting some voltage, maybe 5 volt or something, because Arduino is 5 volt. So let's assume that you are getting just 5 volt, or sometimes some different voltage. So this 5 volt is unloaded right now. When I am saying unloaded, means nothing is connected right now as a load, or I am not connecting any device at the output. If something is connected, then it's loaded, and you have to see what is the input impedance of the device, right? And for that you need to model it, the device, and from the model you can find out Zin using any of the parameter method, and you can keep it here. In general, you must have seen in your, like if you have any circuit like op amp in the books, you must have seen, like if this is a comparator, and here they are keeping something like 50 ohm, or they are keeping 1 picofarad, something like this. If you read any book, this is the standard thing we are saying as a load. Right? So from where these numbers are coming, what do you think? By the way, can I do this one without connecting this? Can I do this? What do you think, Manpreet? Are you following what I mean to say? Because this will be the useful thing for your future also. Yeah, Amol? Yeah, similar to BLC. Okay. Your answer is correct. So from the uh, uh, previous discussion, what I want to say, if you are connecting two things, let's say I am getting some, this is circuit number 1 and this is circuit number 2, or maybe anything which I am going to, maybe oscilloscope, or any device or spectrum analyzer. So when I am going to see the output here, which is unloaded, right now there is nothing is connected, and when this is connected, the output is different, because there is one more resistance which is going to play the role, right? Or your output will decrease because it shared the current. So the real situation is that when you are connecting second circuit, but you cannot do this thing every time. So what you are doing for the simulation, you are trying to mimic what you are going to see in the circuit number 2. So here I know that this op amp, if I am going to do it in my laboratory, I am going to use most probably the probe, whose so probe, if it is 1x, I am going to see something like 50 ohm in shunt with 1 picofarad. But if I am planning to use 10x, then to mimic the 10x situation, I need to make something like 1 mega and 10 power. This is known to me, that's why I am doing this. If it is not known to me and I know what is circuit number 2, if it is known to me, I can add the input impedance of the next circuit. So I need to keep the input impedance of second number circuit. But I need to know what is the input impedance of the second circuit. If I want to find out, I need to use the Y parameter, Z parameter, or whatever parameter you want to use. You keep that and find out the input impedance, keep it here, and then simulate, which is going to give you the real output, or it will not give you, some different results than what you are going to connect two circuits together.
So basically, this impedance arrangement that we are making is to nullify the loading effect.
Actually,
To mimic the loading effect.
To mimic the loading, yeah, because that is the real situation. So sometimes what is happening, if you are connecting here, let's say motor at the output, those motors input impedance is actually very low. So if I am connecting here, let's say something like 10 ohm or 20 ohm, your output will be like earlier you were expecting 5 volt, but after connecting this, it's 0.5 volt or something like that. So you know the situation.
While manufacturing any device,
Mm-hmm.
we will be connecting it with any type of device in future or in any
Yeah.
application. So while the time of connecting, we need to consider this.
So it's depending on your circuit. Maybe I am going to connect this op amp to oscilloscope, or I am going to connect it to some other circuit. It might be just a buffer also. It might be a bigger load also. It might be somewhere just lamp. Maybe have you done that kind of experiment where you are connecting a lamp at the output in power? So maybe in future you will do that where you are connecting a lamp. Done? Yeah, with transformer output is low, your bulb, right? So in power electronics application, most of the time the output, or the one through which the output is taken, is bulb, right? So this has lower resistance actually. So you need to find out what is the impedance. Sometimes you are keeping just a transformer. If you are looking, if your application has a transformer, then we have readily available equation, which is like if it is terminated with inductor or terminated with a capacitor, you know what is the value, right? And these impedances, okay, the most important part, these impedances are not single value, right? So I cannot say that Zin is equal to 5 ohm if I am saying this. If I am saying Zin equal to 5 ohm, it does not mean that it's 5 ohm every place. This is dependent on frequency. This is the value for a given frequency. I'm working at particular frequency. Let's assume that you have a situation, this capacitor, the impedance is, how much is the impedance by the way? If I'm looking into this, its impedance is 1 by j omega c, right? So 1 by j omega c. So c is fixed, but for a different value of frequency, the impedance profile will change, right? For various frequency. If I'm telling you it's 5 ohm, it might be for some frequency, and sometimes it will go to 1 mega also, right? So it depends which frequency you are working in. So your impedance profile will change, right? And accordingly you need to find out the impedance. If you are working at different frequency, you will have different answer. I would have told you this maybe. So I told you about this experiment. If you are going to do this, there will be some problem. If I'm, or maybe okay, I'll give you maybe in some time in laboratory, or maybe in some assignment. I'll give you this just to understand how it's varying with frequency. Okay, right? So it's depending on resistance also, what resistance value or what impedance value. Resistance is fixed. Its impedance profile will not change, but if it is just a resistance, what you are going to see, y2 is equal to nothing but y21 times v1 plus y22 times v2, and v2 is nothing but minus I2R, right? Because the current is going in different direction. So we can find out, or I'm interested in finding out y21, then I can write down v1 in terms of I2 as follows: I2 minus y22 v2 divided by y21. V2 is nothing but I2R, so we're going to see. So therefore you are going to get I2 by V1 is equal to y21 divided by 1 plus y22 times R, and you can divide it by R and you can get this expression, right? If it is terminated with resistance, this is the real situation. So you cannot keep your ports open. It will have some load resistance, and this is equivalent of that resistance. You can keep other things also, like inductor, capacitor, whatever you want to keep. That will give you the output, or that will change the output performance. Okay. Few more things. Where is it? Okay. Some conclusive more remarks are there, where like we are going to solve some of the difficult questions, where what is going to happen where two ports are not just simple two ports, but two ports networks are cascaded. That might be the case, right? Where two T networks are cascaded. We understand what is cascaded, right? Output of uh, output of first part is connected to the input of the second circuit. Then it's called cascaded. So two ports are cascaded. It might be like T network or might be pi network. If they are cascaded, then transmission matrix, which is nothing but an ABCD matrix, is product of two individual transmission two port matrices. Means if there are two ports are available like this, and if I am going to cascade them, let's call this one as V2. So what I am going to do, or what will be my approach, I'll solve this network's ABCD network. I'm going to solve ABCD network for this network, and then I'm going to make the product of both. Product will give me directly the effective ABCD matrix for V1 and V2 port if they are cascaded. Otherwise, no. Otherwise, you need to follow some other technique. So this is also telling you, if two networks are cascaded, you should use transmission matrix, which is faster. One more thing, if two ports are in series, right? We understand series and parallel, right? So if two ports are in series, then Z parameter is summation of individual two ports, because it's effective resistance. I'll keep some examples for you.
So what's difference between cascade and series?
I'll give you maybe some example. So this is, I need to make some. This is called series. called parallel. Piyush. This is called series. This is called parallel. This is called cascade. Right? So all three are different. Right? So if it is in series, of course, it will give addition of two resistances or two impedances, and you have to look at the two individual Z matrices, and you have to make them in addition. Right? Where I went. Okay. There might be one more case where both the two ports are in parallel. If they are in parallel, you have to use Y parameter, and Y parameter will give you the summation of two individual Y matrices. Right? So these three are the important thing when uh, you'll find out most of the networks are actually in cascade or series or in parallel, and we are going to solve those kind of networks. Right? I'm going to give you an assignment. Maybe because I checked, we have only 12 lectures left, so I need to move further. Otherwise, it will be difficult. If you want to do some tutorial, then just let me know. We can have it on Saturday, right? Those who are agreeing, we can have it on Saturday, right? But on regular classes, it's difficult, right? So on Saturday, if you want, we can have it. Okay, and there is one definition which I haven't taught till now, but gyrator, it's not exactly existing element, but gyrator is defined as one kind of element which is impedance inversion device whose input impedance is related to its load impedance by this equation. Means Zin is equal to a square times YL or a square divided by ZL. It's not transformer, by the way, where transformer has a square times ZL. If you are looking into transformer, it's going to see a square times, sorry, n square times ZL, right? Some people can make a and n both equal, or but it's not going to give you same results. But using transformer, you can make the gyrator. Right? This is just a definition. Maybe in future we are going to use it. So just remember, transformer's input impedance is n square times ZL, whereas gyrator's input impedance is a square divided by ZL, where a might be equal to n if you are designing gyrator using a transformer. Right? Okay. So using uh, those three silver bullets, we can say that when two ports are connected in parallel, find Y parameters, because addition of these two are going to give you the effective Y parameter. Similarly, if they are in series, easiest way to use the Z parameter. And when two ports are connected in tandem, the transmission matrix is generally easier to obtain. Right? So when to use which matrix is depending on your application, how you are connecting. However, this is just guidelines. You can use other parameters also through which you can have the answer, but it will take maybe some longer path. Right? When you are solving it, maybe instead of Y parameter, if you are taking ABCD parameter, it will take maybe more number of pages to solve that rather than Y parameter. So this is just a guidelines. However, if you are following these guidelines, you will have answer quickly or quicker than other analysis, right? This is one of the, like, you can see this kind of example. So what do you think, whether it's in series, parallel, or in cascade? Maybe in like tutorial, if you want, we can have it and we can solve more questions. Around 20 questions are available in Franklin course, so we'll take same questions and we'll try to solve here if you want, right? One by one. So what do you think? You have to answer me. I will not give the answer. By the way, these two are T networks, which are So this is effective two ports, right? This might be having V2 and this might be having V1 and this one might be I1, this might be I2, or whatever way you want to do it, you can do it. V1 prime, V2 prime, I2 prime, I1 prime, whatever you want to do. Okay, so if you know which particular like they are in parallel, series or cascade, then you can find out accordingly the parameters. Like if it is in parallel, you should use Y. If it is in series, you should use Z. If they are in cascade, you should use ABCD, because afterwards it's easy, right? You know how to solve this T network. We solved many times, right? Okay, so in that case, we will revisit if you want, right? You just let me know on Saturday if you want the extra lecture on solving just questions, then I'll come prepared accordingly, right? Otherwise, there is new chapter which is starting, and we are going to start with, till now whatever we have done, it's coming under the class called analysis or the circuit analysis, right?
तो उसका आंसर क्या था?
Answer is in next slide, so I'm not giving you. You think about it. What do you think, Pius? Okay. Huh?
Parallel.
Yeah, okay. It might be parallel. It's in parallel, by the way. That's correct answer. Then you should use biparameter. Okay. You should see more and more networks. Otherwise, like the next slide was the answer, but you should look at more networks. I'll show you like many networks are available in many books, or you can create your own networks wherever you want to connect, and you can find out whether it's in parallel or in series. That one was in parallel. So till now, whatever we have learned, it's called analysis, where we know the circuit. Somebody has given you the circuit, and you have to analyze it. How the circuit will respond, or what will be the AC response, frequency response, DC analysis, transient, or anything you are doing for a given circuit, that's called analysis. But if somebody has told you that I want to design a circuit which will have following specifications, because this is the real thing, right? Where somebody has told you that this is the specification, then from the specification, maybe you will do some analysis, but through that you will derive the circuit. This is called synthesis. That is the second part of our course, where you need to derive circuit, where maybe specifications or some analysis is given, or let's say I'm telling you design a circuit where 1 Henry, something like this. So I can design a circuit. Right, whose input impedance is this, right? This was known to me, that's why I kept it. So similar to that, there are lots of way to find out circuit, which we are going to study, where different people have given their different theory, right? Through which we will find out RLC circuits. If somebody is very much interested in something called filter design, this is very important topic. Do you know what is filter design or filter? Hmm? Yeah, so those filters like low pass filter, high pass filter, band pass filter, notch filter, right, or band stop filter, right? We're talking about these filters, but in reality, if they are first order, it's easy. I know that first order is easy, low pass filter. But if it is fifth order, seventh order, eighth order, it becomes difficult. If it is with operational amplifier, it becomes more difficult. But why do you think we need more order? What do you think, Akshat? We understand the difference between first order filter, first order low pass filter, second order low pass filter, or maybe some 10th order low pass filter. What is the difference? All are passing only some low band of frequency, right? So what is the difference in these order? What order decides? Yes, Piyush. Maybe you can keep these equation in your mind and you can draw the Bode plot in your mind. So what is the difference in first order low pass filter, frequency response, and the second order? If I am drawing here frequency with respect to magnitude in first order, maybe I am going to see something like this. What will be the slope here, by the way? Minus 20 dB per decade. What about the second order? What I am going to see here? Minus 40 dB per decade. What about third order? Minus 60 dB per decade. Or if it is infinite order, I am going to see something like this, right? So the slope is infinite. Then this will be the situation. So it's depending on how much steeper response do you need. Depending on that, you can design the required number of order. Let's assume that you are like, have you ever heard radio mirchi is not possible here, but if you are hearing some radio station, sometimes you are hearing some other stations also, like two songs you are hearing at a time. When I want to save this, means at, what is this, maybe 91.9 FM and maybe somewhere, right? So this is frequency bands are available, right? So these frequency bands, they are near to each other. They are allotted only to this radio station, which are known as FM, or the frequency modulated bands, where I am interested only in, let's say if I am hearing 91.9, so I am only interested in 91.9. I am not interested in other band which is very much nearby. But if you go nearby, you will hear this one also. If you are tuning it, instead of 91.9, if you are hearing 92 megahertz, then you will hear this one also. Or maybe if you go here, you will, or if you are in between here, you can hear both of them. Why this is happening? The one who is designing this, he is actually using a band stop. I don't want to hear anything else, let's say. And he, like I'm taking care of, let's say, just 91.9 FM. This is my band. So what I want, I'll keep one band pass filter, just allowing me to hear only 91.9 FM. But I don't want to hear this one. But still, you can see this part is there, where if something is happening here, it will be here also, right? So you can listen those bands inside your band, and this is happening because you cannot make infinite order band pass filter. If you are going to make it, you will use maybe 6th order, 7th order filter. It will be like this, right? Where you can hear this one also, which is allowing frequency, right? It's not zero. When you are hearing at your speaker will try to look at everything. It's not just designed for 91.9, right? So you are hearing from here to here, whatever is there. So maybe the low amplitude, something called 93 FM, is also audible to you, right? So if such kind of things are there, then you need to design higher order filter, and this is very important design. Mostly like those art, DRDO people, they need some good design engineer who can design filters for them, for even radar application. They need it, and they are designing good filters. So if I'm telling you the specification that I want to design it for this frequency, and I want to hear just like this frequency and other frequencies which are in nearby, uh, they are these frequencies. So from that you can find out the order of the system, and from order of the system you can find out the circuit also. That synthesize I am talking about. But what we are studying is all about the passive components. It is not active, it is only for passive components, and same theory can be extended for the active component which is using op amp, and it can be used for other courses or other things which might be digital, and you can study same thing maybe in DSP, which is full-fledged one course only on filter design. Hmm? Yeah. So it's only about filter design, where you are designing filters, right? It's a next level course of signals and system, but intermediate knowledge of this network theory is important to understand how this DSP works. So if you are interested in filter, you should go for DSP, right? And afterwards you can go to image processing, speech processing, so many things. So all the people who are working here and on image processing or signal processing, they are actually dealing with these subjects, right? Okay. So same book I'm following, Franklin Co. So throughout semester now, like there is no other book which is going to be used. So chapter number 10. So before making the circuit or synthesizing the circuit, we should know that whether your given specifications are possible to realize it or not. So it's a mathematical problem. First of all, we need to find out whether this circuit is realizable or not. So before doing anything, you need to declare that yes, it's realizable. Then you can proceed further. Otherwise, you should not proceed. You should say that no, your specifications are not good, or it's not feasible to make the circuit. So I'm not going to make it. So you have to go accordingly, right? So first of all, we need to understand two things. One is called causal, and one is called stable. If these two cases are not there, we are not going to design the circuit. We are going to say that your circuit, I cannot make the circuit, because if it is not causal and if it is not stable, it's not following the realizable category. So if it is realizable, have you studied causal in signal system? Right? So what is causal? There are two possibilities, A and B. So which one is causal system and which one is non-causal? This one is what? Not non-causal, right? And this is causal. So yes or no? Yeah. Huh? B is causal. Okay. Or if you want to change, I don't know. So generally, at so if we are going into the definition, so if you are looking at the impulse response, then impulse response must be 0 at t less than 0. If that is the case, it's causal. So in this case, this is causal, but this is not. Right? Maybe some other way also to look at the causal system. Some mathematical proofs are there, but we are not going into that. I believe that you have studied maybe in signals and system, but by just to check whether it's causal or not causal, you have to look at the impulse response, right? So one more thing. So this was one of the condition. Second one is called stable. So before this course, did we talk about stable ever or no? Oh, okay. So stability is dealing with the output, how much uh, how much ripples are there in the output. This is going to be deciding the stable. But there is one more thing. If you are going systematically, there is something called BIBO system, which is known as, yeah, so you know about this. Okay, so it's called bounded input, bounded output. So what do you mean by this? Yeah, we understand these words, but what is the significance of this? The response stay within the limit. So if this is my input, so this is my bounded input, I know. Let's assume I'm giving 1 volt with respect to time, and the output is in this way, or it might go this way. So which one you say that it's not bounded output? Yeah, this green part is not bounded output because it will give the output till maybe VSS to VDD only, or plus V supply to minus V supply. So this is oscillating output and it's not stable. Right? There are many other theory through which you can say stability. Just to find out stability, there is one complete course called control theory, through which you can find out whether the system is stable or not. All the chapters just deriving the stability theory in different way. So this was just one crude way of the starting whether the system is stable or not. But other ways are also there, like using Bode plot. By looking at phase margin, you can predict whether the system is stable or not. Similar to that, there are other plots, other techniques through which you can find out. And for all of them, we are looking at whether the system is stable for a given bounded input, whether it's bounded output or not. If it is not, then it's unstable system. So in both the cases, you need to say that if it is not BIBO stable and if it is non-causal system, you should not proceed further, right? So you should declare that the uh, system is not realizable. Uh, some part of this topic was also in your first year IC 161. So when I was teaching this to first year, and I don't know, Priyanshu Khandelwal, or what is it? Priyanshu, the singer, right? Who has already graduated. So I asked one question on realizability. Hmm? Priyanshu, right? Priyan Saxena, yes, Priyan Saxena. So I kept one question, and unfortunately, like the question was wrongly framed, and he found out, sir, this cannot be realizable, and I cannot make the circuit. Except him, like all got 0 marks because he was correct, and everybody were trying to make the system which is realizable, right? So you should find out the real answer. You should not look at, like, because I generally don't solve the questions right before giving. So look at the theory, and if it is not realizable, you should say that it's not realizable. Every time, every time you cannot have the circuit as the output. Okay, there is one more thing which is already known to us. I'm not looking into poles and zeros. You know what is poles, zeros, uh, DC gain, all these things are known to you. If you have a circuit, if you have a transfer function written in the Laplace domain, then h of s cannot have poles in the right half plane. This is basic criteria for stability. I'm writing few more criteria. So if they are in right half plane, the system is unstable because it's not going towards 0, but it's the progressively the output will increase and it will oscillate if it is on right half plane. H of s cannot have multiple poles in the geometry axis. When I'm saying this, what I mean to say, you may have the circuit which is like this, and this is also a filter. This system is stable or unstable? Can you write down the equation or the transfer function? Yeah. So what do you think? I'm drawing the pole 0 plot, yeah, yes or no? Is correct? Yeah. So this system is stable or unstable? Hmm? Why it is unstable? So we agree that they should not be in right half plane. So where should I consider this line? It will be oscillating, but it will oscillate with fixed amplitude, right? It's fixed amplitude. It's not decaying or it's not increasing, right? So such kind of system is known as marginal stable, or it's also like it's partial stable. So let's keep considering that system as stable, right? Even though in your circuit you will have inductor and capacitor, which is going to give you marginal stable output, you are going to consider that one as stable. Otherwise, you will not able to design any system because you will have all RLC circuits, right? So we will consider this one in marginal stable or stable condition, and we'll make this budget that how much oscillations you will have. You can make the budget, or you will design a circuit such a way that this oscillation is within your limit or the specifications given to you, right? So, but if there are multiple multiple poles on j omega axis, this is not going to be like uh, not the smaller one, but the amplitude will be higher on. It's going to be multiplied by a0t. If you remember the Laplace, if it is right, if you remember the Laplace, it will be multiplied with the the value of amplitude times t. That will be right. So in such situation, to avoid such situation, we are saying that h of s cannot have multiple poles on the j omega axis. If it is there, please stop, or try to keep poles somewhere nearby. Means if it is 0, a0 and a1 are nearby, then it's okay, fine, you can design it. And one more thing, the degree of the numerator uh, cannot exceed the degree of denominator by more than unity. So zeros has to be lesser than poles. If they are more, then you cannot design it. Actually, you can design it, but it's not able to design in our course. Right? In DSP, it's possible. We will learn it something called finite impulse response, FIR filters. You can design it. Right? But for this case, it's not possible. What we are designing for that, it's not possible. Okay. And there is something called one more criteria, but it's better we will talk about this maybe next time. But are you following till now? Okay.